we're always dealing with this ICE kind of. It's kind of like ICE. It's just, you know, different type of form of that. So we're going to do this problem. And the first thing we'll have to do is we're going to have to find our concentration of our ions that form the precipitate. So first thing, this is a problem that we're going to have to identify the precipitate. And then maybe you guys can tell me what the precipitate is going to be based upon solubility rules. Kind of see what it's going to be. So we got a reaction that we're going to do. Okay, and so our reaction is CaCl2 aqueous plus AgNO3 aqueous. So what's our products? Double displacement. Tell me what the products are. One product.
CaNO3.
Okay, so we got CaNO3 2.
Yep.
And then what's our other product?
AgCl.
AgCl. Now you guys got to look up charges and that, and make sure their charges are balanced out. So that's that whole look at a double replacements, and then you got to decide which one of those two is probably your solid. CaNO3 2 or AgCl?
AgCl.
Oh, all right, good job. So why AgCl?
NO3 is soluble.
Yeah, NO3. You guys know NO3 is pretty much always soluble, so you know that's aqueous. So then the only one that can form a solid is AgCl. That would be right. Okay. We got to figure out though if it's going to form a solid, because it could be dilute enough that where it's not going to form a solid. So what information do we have to know? Do you guys have your book? Do you guys have the KSP for AgCl?
Well, 1.6 times 10 to the negative 10.
That's for AgCl, right?
Yes.
Okay. Now, if we come up with, when we plug in our molarities, if we come up with a number greater than that, then it's going to be a cloudy. When we put these two solutions together, pour them together, it's going to be cloudy. If the Q is smaller than this, then it's going to be clear. So we can see if it's going to be cloudy or clear that we're going to have. So we've got to find the molarity of what two ions? So we got to find the molarity of what two ions do we need to know the molarity for? Yeah, we've got to find the molarity of what? Ag ions? And we've got to find the molarity of what other ions? Chlorine ions, right? You guys, I'm going to let you guys work on that, and we'll see what you come up with. So I need you to tell me the molarity of silver ions based upon our original solutions, and I want you to tell me the molarity of our Ag ions given the original solutions. Go ahead and do that. You guys should be able to do that. Is that what you guys got?
Can you show me?
Yeah, I'll show you how to do it. But silver, I came up with if I did it right, 0.0027 molarity. Okay, so I'll do that one, and maybe you'll have to readjust chlorine and how you do it. So I know I've got 0.053 molarity of AgNO3. And so I'm going to multiply it by 0.01. What's that give me? When I take 0.01 liters times 0.0053 moles over liters, I get how many moles of AgNO3, right? So the number of moles I have of AgNO3 is 0.00053, right? One more zero. Should be 5.3 times 10 to the minus 5. So Okay, and that's moles, moles of Ag and NO3, right? Because it splits into 1-to-1 ratio. So then if that's 0.00, then what I can do with that is divide by 0.02. Because that's the new volume, right? So I got 5.3 to the -5 silver ions in 20 milliliters or 0.02 liters. So did I do the math correct on that one? Is that what you get? When you divide those out, will I get 0.0027? Okay. So do chlorine and see what you come up with chlorine. You guys should be used to kind of manipulating moles, dividing by the new volume. We did that on titration. You guys were doing that on titration and different stuff. It's kind of a trait that you see. 0.00265. I just rounded to 0.0027. Chlorine you got to be careful with because it's a 1-to-2 ratio, right? Because when you divide this CaCl2 down, you're going to get twice as many chlorines as you do calcium. So it's kind of like your 2x. I mean, whatever your concentration is for the original solution, you have to double it because you're going to double the number of chlorines forming the solution. So on this next one, I came up with an answer that's 0.0015 molarity. Anybody questions on that? So what you do, I'm not going to write it out because I'm getting, but you do it just like the other one, and you take 0.0015 times 0.01, which would give you 1.5 to the -5th. So this would be 1.5 times 10 to the -5th moles, once you multiply that out. So then chlorine has to be double that. So then I would take that divided by 0.02 and I get my concentration, right? For every 1.5 to the -5th moles I have of CaCl2, I get double the moles of chlorine. It's always been the case when we have X, 2X. So then what do I need to do with that to find my Q? So KSP equals what? The concentration of silver ions, right? Times the concentration of chlorine ions, right? And then you square it. Is that correct? Right? Because we know that, no, it wouldn't be squared.
Is it one? Oh wait, no, it wouldn't.
No, it wouldn't be squared. Sorry. Okay. I'm thinking it'd be squared. It'd just be that, right? Right? AgCl, we know, breaks apart into silver ions and chlorine ions. So it'd just be Ag concentration times chlorine concentration. But we're going to get a Q on this, though, because we don't know where it's at. So this would actually be Q is equal to the concentration of 0.0027 molarity times 0.0015 molarity. So what do you get when you do that? Anybody got an answer? -6?
Yeah.
Okay, what'd you get with the number out in front?
4.1 times 10 to the -6.
Can we get something different than that? Is that what you guys got? So is it going to form a precipitate, yes or no?
Yes.
Yes. Q Q is greater than KSP. We put those two solutions together, we get a number to the -6, KSP's to the -10th. It definitely precipitates out. Now, if I came out with an answer that was like 4.1 times 10 to the -12, no precipitate forms. Questions?
So why is it not squared? Why is CL not squared?
Because when we do this, this would be X, and this would be X.
So you're just focusing on that part then,
Yeah.
not the entire
Yeah. So it would be X squared. Yes?
Why don't you have to determine what's the limiting pull out?
That's a good question. I got to thinking that. He's asking, how come you don't have to determine what's limiting? And the reason why you don't is because we're not focused on the precipitate and how much we're getting out. So if we were focused on the precipitate and how much we're getting out, then we might take a look at limiting. But these are two concentrations, and we say that KSP is equal to those concentrations. So guess what? Eventually, this is what happens. The solution will be saturated. Do you guys agree with that? If anytime you got to precipitate, the solution's saturated, correct? Anytime you can't dissolve more of something, it's saturated. So we know that the concentration of the solution, or the concentration, we know that it's going to be saturated, but we have some solid in there too. So all this is telling us is if it's going to form a precipitate or not. We don't have to determine how much of the precipitate forms or any of that. That's why, I don't know if that answered your question, but that's...
I'm still sort of confused, but I guess.
I know what you're, usually when we do this, we look at which one's going to run out, right? Okay, and you can't do that with one of these reactions where they're at equilibrium. Okay, because what will happen, if we got too many of one ion, which we do, then what's going to happen, it's going to shift to the left and form a solid until it gets back to saturated level, right? Now if these two are a low level, such a low level they don't form a precipitate, on that, you know, it's just going to be a solution and it's not going to be saturated. So, Calvin, at that point it's not saturated, so we can't have it equal to KSP because it's no longer saturated. This is only based upon saturated solutions.
Mr. Garland,
Yes, ma'am.
this is probably a really dumb question.
No, it's probably not.
So were we just finding, okay, so we're finding